All right, welcome to Physics Video 5.2. We're going to learn about conservation of momentum. Again, we're going to kind of do things a little backwards from how I usually do. We're going to really focus today on solving the problems. We're not going to worry quite as much about the concepts, but we're going to focus on how you use conservation of momentum to solve a problem. And then in class, when I see you, we'll talk a little bit more about sort of the concepts and what all of this means, okay? So the objectives behind the video today are, number one, to be able to explain what the law of conservation of momentum says, and secondly, to be able to use that law to solve problems. Okay, so here we go. The law of conservation of momentum up here at the top of the screen tells us that in the absence of external forces, the total momentum of a system always remains constant. Okay, so for that to make sense, I got to define a couple other things. First of all, system. What do we mean when we say system? The system, in this case, is going to represent just a collection of objects, all right? Usually what's going to happen when you talk about conservation of momentum is you'll have either two objects that are colliding, where you'll have two objects that are originally separated running into each other, or you'll have them exploding, which means they're originally next to each other and then pushing apart, okay? So regardless, the system is the objects that are interacting. It's the objects that are either pushing apart or running into each other, okay? Now, an external force is a force that's applied by an object that's not in the system, okay? So usually when you're talking about conservation of momentum, what you would do is you would just define your system to be all of the objects that are applying forces on each other, all right? So based on that, you've got this collection of objects that are, either running into each other or pushing off of each other or whatever. All right, and what the law of conservation of momentum says, here it is in text. In shorthand, it's this. The total amount of momentum that you have initially, in other words, before those objects interact and exert forces on each other, is equal to the total amount of momentum that you have after they interact. Okay, so remember this Greek letter sigma here, we've used it to mean net before, right? When we talked about net force, right? The word net just means total, right? So this is total momentum, and then the I means initial before they interact, and the F means final, means after they interact. All right, so this is probably easiest to understand if I just do an example, and I'm actually going to do the first example 2 different times. The first time I am going to at least try to introduce you to the concept, and then I'm going to go back and show you sort of a more streamlined way of solving it. Okay, so here we go. We've got a 1,200 kilogram truck that's rolling at 5 meters a second. It's going to collide head-on with a 500 kilogram car going at 8 meters a second. Since it's a head-on collision, that implies that they're moving towards each other. Okay. All right, so the car and the truck are going to collide, and then after the collision, immediately after the collision, the car is going backwards at 3 meters a second. So the truck has sort of forced it back. And our job is to find the final velocity of the truck. All right, the first thing I want you to do is make a drawing, and your drawing should organize all of your information. This is majorly important, A, because it shows me that you understand what's happening in the problem. B, it's going to force you to think about the directions that the objects are moving. And remember, the direction is important, right? Because as we learned, all throughout the year, I guess, really, you got to keep track of your signs, right? And if the object is moving forwards, that's going to be positive, and backwards is negative. Okay, so let's start by making a drawing. All right, so there's my drawing. I'm going to, in addition, use this drawing to help me organize the information. So I'm going to write down what I know. 1,200, whoa, that was not what I wanted to happen. We've got a 1,200 kilogram truck. So mass of truck equals 1,200 kilograms. It's rolling at 5 meters a second. So here's the velocity of the truck initially. It's 5 meters a second, right? Don't let the subscripts confuse you. This is telling me its velocity. That's how fast the truck is going. T is for truck. I is for initially, meaning before the collision. Okay? Now it's colliding with a 500 kilogram car. So mass of car is 500 kilograms. And it's rolling at 8 meters a second. Velocity of car initially, right? Velocity car initially is 8 meters a second. And the drawing helps me identify, oh, wait a minute. that's got to be negative, right? Because it's moving in a negative direction, okay? Immediately after the collision, the car is going backwards. So the car is going to get forced back this way. So here's the velocity of the car final meaning after the collision. It's 3 meters a second, and you got to be careful here. A lot of people look at this and they see the word backwards and they think, oh, it's got to be negative. But based on my drawing, backwards is actually in a positive direction, right? Because it's going to the right, and right is positive, right? So that's actually positive 3 meters a second. All right, and our goal is we're trying to find the velocity of the truck final. Okay? So that's everything that we know. Now, to solve it, we're going to kind of make a chart, actually. I just saw this done this way recently, and it makes a ton of sense to do it this way. So here's what we're going to do. We're going to make a chart, and on one side of the chart, we're going to list our objects. So in this case, we've got truck and car. Those are our two objects. Okay, and then what we're going to do is we're going to keep track of their momentum both before, in other words, initially, and after the collision, in other words, final. Okay, and we're going to find the momentum. All right. While I'm at it, I guess we're also going to, well, we'll do that at the end. Okay, so here we go. The momentum of the truck before. So the momentum of the truck initially would be, well, remember, you guys, momentum is mass times velocity, right? Whoa, that was weird. Momentum is mass times velocity. So our truck has got a mass of 1,200 kilograms and a velocity of 5 meters a second. So multiply it out, and I'm going to get 6,000 kilogram meters per second, right? Okay, now I'm going to do the same thing for the car. The momentum of the car initially would be its mass, 500 kilograms, times -8 meters per second. And that gives us -4,000 kilogram meters a second. I'm realizing also, hopefully you caught this, I will circle it in green and then fix it. That number there is wrong. It should be 6,000, so let me fix that. Oops. Sorry about that. That should have been 6,000 kilogram meters a second. Okay, so what do all these numbers mean? Well, this number here represents the momentum of the truck before the collision, and this number represents the momentum of the car before the collision. Now remember, what conservation of momentum tells us is that the total momentum can't change, right? Because the only forces are the car pushing the truck and the truck pushing the car, so we don't have any external forces. So our total momentum initially is 6,000 from the truck plus -4,000 from the car gives us 2,000 kilogram meters per second. That's our total momentum before the collision. All right? So what conservation of momentum says is that our total after the collision also has to be 2,000. Okay? So let's see if we can figure this out. Now, let's take a look at what's going on after the collision. All right? After the collision, we're missing some information. If I wanted to find the momentum of the truck after the collision, I'm going to get stuck because I don't know the velocity. So what I'm going to do is I'm just going to leave that as a variable. Okay? So I'm going to take the 1,200 kilograms, that's the mass of the car, and multiply it by the velocity of the truck final, because that's what I'm looking for, right? So this is what I'm trying to find. All right? The momentum of the car I can find now. The momentum of the car final is just the mass of the car, 500 kilograms, times its velocity, 3 meters a second, and it gives me 1,500 kilogram meters per second, right? Cool? So what that means then is my total momentum final is those two things added up. The two things that I've written in green added up. It's 1,200 kilograms times VF plus 1,500, right? So I just added those two up. Okay? So we are almost done here, you guys. Check it out. Conservation of momentum tells me the total momentum before the collision is equal to the total momentum after the collision. So here we go. Total momentum before the collision is right there, 2,000, right? Well, that's got to equal the total momentum after the collision. That's this. Right? Okay. So solve it. A little bit of algebra. We got to subtract 1,500 from both sides. And you get 500 equals 1,200 times VF. Divide both sides by 1,200. And we get a final velocity of our truck. Is that what we were looking for? I don't even remember now. Yes, final velocity of the truck. Oh, sorry. You can call it final velocity of the truck or the truck's final velocity. It doesn't matter. So anyway, 500 divided by 1,200 gives you 0.417 meters per second. Cool? So there you go. Now, to be honest, that's probably the best method because it's very conceptual and it relies on this idea here that your total momentum is constant. All right? That said, there's sort of a more streamlined way of doing it, which is this. Okay, so we're going to solve it again. I'm going to, off to the side over here, do a little bit of algebra. All right, so check it out. The whole idea is that our total momentum before the collision has got to equal our total momentum after the collision, right? That means that the momentum of the car initially plus the momentum of the truck initially has got to equal the momentum of the car final plus the momentum of the truck final. Remember, momentum is mass times velocity. So this becomes the mass of the car times the velocity of the car initially plus the mass of the truck times the velocity of the truck initially, right? That's this and this equals the mass of the car times the velocity of the car final plus the mass of the truck times the velocity of the truck final. Okay, so what we've got here is one giant equation, right? Some of you are looking at this and going, whoa, what just happened there, right? But the nice thing is this equation can be used to solve any of the problems. Anytime you've got two objects interacting with each other, colliding or exploding from each other, you can use this equation. Now, it might not be a car and a truck. It might be, you know, an apple and an orange, or a penguin and a cow, or, well, you know, whatever your two objects are. But this equation is basically how we're going to solve this. All right? So, in this problem, let's take a second to write down what we know. So here's what we know. We know the mass of the car is 500 kilograms. We know the mass of the truck is 1,200 kilograms. We know the velocity of the truck initially was 5 meters a second, and the velocity of the car initially is -8 meters a second. We know the velocity of the car after the collision is 3 meters a second, and we're looking for the velocity of the truck after the collision. So you'll notice there are here 1, 2, 3, 4, 5, 6 variables. We know all of them except for one. So plug them into the equation. Check it out. I'm going to plug them in. I'm not going to worry about units until the end because everything's metric. So mass of the car, I'm just plugging in these numbers here. Okay, mass of the car is 500. Velocity of the car initially is -8. Mass of the truck is 1,200. Velocity of the truck is 5. Equals mass of the car, 500. Velocity of the car final is 3. Plus mass of the truck, 1,200, times velocity of the truck final. And solve it. It's just algebra. So you're going to get -4,000 plus 6,000 equals 1,500 plus 1,200 VF. Okay, so this accomplishes the exact same thing we just did on the last slide, but with a little less thought, I guess. Because when you're using this big equation, it's just plug and chug, and you know. All right, so subtract your 1,500 from here. The math is the same as the last slide, so I'll let you rewind it. Okay, so one other quick thing here. In this example, the objects did not stick together, right? The two cars collided, one of them slowed down, the other one got pushed back. The objects did not stick together, all right? A common thing that happens in collisions is your two objects will collide and then stick together, right? Like two balls of clay smacking into each other, right? That's what's called an inelastic collision. So I want to show you how to solve that. All right, so example 2 is the same as example 1, but this time instead of giving a final velocity of the car, they stick together. So we've got a 1,200 kilogram truck rolling at 5 meters a second. It's going to collide head-on with a 500 kilogram car rolling at 8 meters a second. During the collision, the two vehicles stick together, and we're going to find the velocity at, oh, this is supposed to say which they're moving after the collision. So here's what we know. We know the total momentum before the collision is the same as the total momentum after the collision. That means that the momentum of the car before the collision plus the momentum of the truck before the collision has got to equal the momentum of the car after the collision plus the momentum of the truck after the collision. So mass of car, velocity of car initially, plus mass of truck, velocity of truck initially, equals mass of car, velocity of car final, plus mass of truck, velocity of truck final. And plug in your numbers. All right, and I'm, in the interest of time, being a little lazy here and not making my drawing. I really should have, but I want to make sure I stay under my 20 minutes. So here we go. We've got our 500 kilograms for the car. Velocity of the car was, once again, -8 meters a second. Mass of the truck is 1,200 kilograms. Velocity of the truck is what we're looking, no, it isn't. It's 5 meters a second, sorry. That's got to equal the mass of the car, 500 kilograms, times the final velocity. And the truck is 1,200 kilograms, times its final velocity. But notice, here's the big deal, you guys. Since the vehicles stick together, that means they're going to have the same final velocity, right? Right? If two objects are stuck together, they've got the same velocity, right? So I'm not going to distinguish between truck and car here. Notice I didn't write VTF and VCF. I just put VF. All right, so look what happens, you guys. This is actually pretty easy. You get 500 times -8 gives you -4,000, plus the 1,200 times 5 gives you 6,000, equals, check it out, you guys know this. Look, quick side note. I'll do it over here in red. What's 5x plus 3x? Isn't that 8x? So what's 500 VF plus 1,200 VF? Oh, that's 1,700 VF, right? Cool, let's solve it. So let's say -4,000 plus 6,000 is 2,000, equals 1,700 VF. Divide both sides by 1,700. And your VF is whatever that divides out to, and it gives you 1.18 meters per second. All right, so there you go. We will talk more about the concepts of this when I see you in class next. All of your problems can be solved basically using, oh, that's not what I wanted to do. Oh no, 20 seconds, almost out of time. All of the problems can be solved using that equation right there. All right, very good, very good.